11.10 Taylor and maclaurin series. In the preceding section, we were able to find power series representations for certain restricted class of functions. Here we investigate more general problems. Which functions have power series representations? How can we find such representations? We start by supposing that f is any function that can be represented by a power series. Definition 1. F of x equals c sub naught plus c sub 1 open x minus a close plus c sub 2 open x minus a close squared plus c sub 3 open x minus a close cubed plus c sub 4 open x minus a close to the fourth power plus ellipsis. The absolute value of x minus a is less than big R. Let's try to determine what the coefficient c sub n must be in terms of f. To begin, notice that if we put x equals a in equation 1, then all terms after the first one are 0, and we get f of a equals c sub 0. By theorem 11.9.2, we can differentiate the series in equation 1 term by term. Equation 2, f prime of x equals c sub 1 plus 2c sub 2 open x minus a close plus 3c sub 3 open x minus a close squared plus 4c sub 4 open x minus a close to the power 3 plus ellipsis. The absolute value of x minus a less than big R, and substitution of x equals a in equation 2 gives f prime of a equals c sub 1. Now we differentiate both sides of equation 2 and obtain equation 3. F double prime of x equals 2c sub 2 plus 2 times 3 c sub 3 open x minus a close plus 3 times 4 c sub 4 open x minus a close squared plus ellipsis. The absolute value of x minus a is less than big R. Again, we put x equals a in equation 3. The result is f double prime of a equals 2c sub 2. Let's apply the procedure one more time. Differentiation of the series in equation 3 gives equation 4, which is the third derivative of f of x, or f triple prime of x, equals 2 times 3 c sub 3 plus 2 times 3 times 4 c sub 4 open x minus a close plus 3 times 4 times 5 c sub 5 open x minus a close squared plus ellipsis. The absolute value of x minus a is less than big R. And substitution of x equals a in equation 4 gives f triple prime of a equals 2 times 3 c sub 3 equals 3 factorial c sub 3. By now you can see the pattern. If we continue to differentiate and substitute x equals a, we obtain f to the nth derivative of a equals 2 times 3 times 4 times ellipsis n times c sub n equals n factorial times c sub n. Solving this equation for the nth coefficient c sub n, we get c sub n equals f to the nth derivative of a over n factorial. This formula remains valid even for n equals 0. If we adopt the conventions that 0 factorial equals 1 and f to the 0 derivative equals f, thus we have proved the following theorem. Theorem 5. If f has a power series representation expansion at a, that is, if f of x equals the sum from n equals 0 to infinity of c sub n open x minus a closed to the power n, the absolute value of x minus a less than big R, then its coefficients are given by the formula c sub n equals f to the nth derivative of a over n factorial. Substituting this formula for c sub n back into the series, we see that if f has a power series expansion at a, then it must be of the following form. Equation 6, f of x equals the sum from n equals 0 to infinity of f to the nth derivative of a over n factorial open x minus a closed to the power n equals f of a plus f prime of a over 1 factorial open x minus a closed plus f, the second derivative of f of a over 2 factorial open x minus a closed to the power 2 plus the third derivative of f of a over 3 factorial open x minus a closed to the power 3 plus ellipsis. See the sidebar. Taylor and maclaurin. The Taylor series is named after the English mathematician Brooke Taylor, 1685 to 1731. And the maclaurin series is named in honor of the Scottish mathematician Colin Maclaurin, open 1698 minus 1698 to 1746. Despite the fact that the maclaurin series is really just a special case of the Taylor series, but the idea of representing particular functions as sums of power series goes back to Newton, and the general Taylor series was known to the Scottish mathematician James Gregory in 1668 and to the Swiss mathematician John Bernoulli in the 1690s. Taylor was apparently unaware of the work of Gregory and Bernoulli when he published his discoveries on series in 1715 in his book Methodus Incrementorum Directa et Inversa. Maclaurin series are named after Colin Maclaurin because he popularized them in his calculus textbook treatise of fluxions, published in 1742. Back to the text. The series in equation 6 is called the Taylor series of the function f at a, or about a, or centered at a. For the special case a equals 0, the Taylor series becomes equation 7, which is f of x equals the sum from n equals 0 to infinity of the the nth derivative of f of 0 over n factorial times x to the power n equals f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial x squared plus ellipsis. This case arises frequently enough that it is given the special name, the Maclaurin series. Note, we have shown that if f can be represented as a power series about A, then f is equal to the sum of its Taylor series, but there exist functions that are not equal to the sum of their Taylor series. An example of such a function is given in exercise 84.